Okay, so let's go ahead and get started. So first of all, this announcement, I think you probably have noticed that I'm recording lectures. And I started doing this for the first time last quarter in my CP133 class. But I just want to mention that it's still sort of experimental. Like I can't guarantee quality of these videos. Okay. I mean, I think if you talk to somebody in CP133, most of the videos came out okay last quarter. But there's sort of this dilemma where to get the best resolution, using Zoom, there's some settings that ITS set for me that sets it up for the best, resolution video-wise. But to get the best resolution, I have to record to my computer, right? If I record to the cloud, the internet connection can affect the resolution. So that was happening last quarter that even though it's very clear when I look at the computer here, as far as what's on the board, after it gets uploaded, it's not as clear. Okay. But see, the dilemma is when I record to my computer, it doesn't put in captions automatically. Where, if I record to the cloud, Zoom puts in captions. And that's a problem because, if I put videos for class that's available without captions, that violates the ADA or American Disabilities Act, which I don't want to do because I get in a lot of trouble. So anyway, the bottom line is, well, since then I've learned that I can actually upload these to YouTube. So I thought YouTube had a restriction on the length of the video, but supposedly you can upload something that's like a couple hours or more long, which I was surprised about. And YouTube does the automatic caption. So anyway, that's what I'm going to do. I'm going to upload these to YouTube, but just have the understanding that I only have certain control over, certain amount of control over the video resolution because it depends on the internet connection, and I don't have control over that. Also, and this is really strange. One time last quarter, the audio for some reason came out all garbled for one of them. I have 3 sections a day, so I make 3 recordings a day, and all the lectures last quarter, and just one came out garbled. And I had the settings all the same. I tested it out like that. So I don't know what happened. And what's really strange is the last meeting we had, meeting 2, for your section, they keep out garbled again. And all the other sections were fine. So I don't know why it does that every once in a while. Like I said, I don't accept the settings all the same. So anyway, bottom line, even though I'm recording these lectures, it's not a guarantee. Like if you miss a class, I can't guarantee that the lecture is going to be the same quality as it was in person. And I think most of the time it will be at least close. Okay, but sometimes, like I said, if the audio gets all garbled, I guess one thing I could do is, if you missed that lecture and one of my later lectures came out okay, I could give you the link to that. It won't be your class, it'll be a different class, but it could be the same material. So that could be a workaround. Right. Anyway, I just wanted to put that out there. Also, the other thing I wanted to mention is next class on Thursday. That's when I'll pass out the form where if you want to stay in the group that you're assigned on the first day, you can just check if you want to stay in that group, or if you want to change, you can check if you want to change. I wanted to wait some next class because as you know, it has dropped into yesterday. So who's in the class now should pretty much be the people in the class throughout the quarter. All right, so today what we're going to do is we're going to talk about the hardware that's in the Otter. So again, each table has a diagram of the Otter. You might have your own too. If you have your own, want to take that out, or you can look at it on the computer because it is on Canvas. It's under Otter Resources. It's the Otter architecture diagram. So the piece of hardware that you're going to be building, modeling in either System Verilog or Verilog is the program counter. And really the program counter is a combination of a register along with a mux. And the good news is you cover it, or you cover it anywhere in CP133 on mux and a register. Okay. So most of what I'm going to talk about here at the beginning of class is just review the share of 133. Okay, because really what you have to do is a lot of what you did in 133 to build this program out. So I want to start over here with the MUX. Now, MUX is an acronym for multiplexer, and this is the symbol for the MUX. And a MUX always has multiple inputs and only one output. So what I'm showing on the board there is an example of what's called a 4-to-1 MUX. So there's 4 inputs. There's 1 output. But you can also have a 2-to-1. That's a lot of you. I should say the people in my 133 class, some of the instructors from 133 do different things. But people in my 133 class, we had a 2-to-1 MUX in the couple of the designs that we had in that class. So you can have 2-to-1, 4-to-1, 8-to-1, and so on. So can anyone tell me how the MUX works? I mean, we have these multiple inputs coming in, and we have one output going out. So, I mean, what's the MUX doing? Exactly, yeah. Whereas the other input is SEL, stands for select. And based on the value, like it's going to choose one of these inputs and connect it together. So since I'm choosing from 4 inputs, how many bits would that select input have to be? In order to choose from 4 things, how many bits would I need? And, right, again, that goes back to the number of values, to the number of bits. Two bits, I can have 4 values, right? 0, 0, 0, 1, 0, 1, 1. So you see the select line. Remember how we distinguish multiple bit input and output with the slash and the number, right? And that number. Okay, so we made a little table of how this was operating. Where one side is our select input, the other side is get out. Well, I have a 0, 0. I'm selecting whatever's on this 0 input. So I will just get a 0 input out. I've got a 0, 1 here. Let me get whatever's on the 1 input. I have 1, 0. I get whatever's on the 2 input. I have 1, 1. Get whatever is on this. Switch. I think that it's like electronic multi-position switch that it's choosing from multiple inputs. Now, by the way, the thing was the same. These are all worth it. It's just whatever input is selected, that's what gets connected to the output. So, do you have any questions on how that works? Now, if you take a look at that otter diagram, can you tell me how many muxes are on there? There's quite a few, right? Like 5, 4 or 5, something like that. So there's quite a few muxes as part of that otter diagram. Okay, now system Verilog, if you wanted to model a mux, now, if you were in my CP 133 class, when we modeled a mux there, we used the if statement, and I had to use a if statement primarily because also in that class, the decoder that we modeled kind of called for a case statement. So just to give a variety, I said use the if statement for months, because there was only a 2 to 1 months. Well, in this class, I would rather, again, you can do whatever you want, but I would rather that you use a case statement for the months. You're going to see you're going to need a if statement or something else. So just kind of vary it a little bit so people aren't always using a case or always have a little variety. Anyway, if you're going to use a case statement for this class, here's the Verilog. Now I'm just going to kind of outline this, and I'm going to use system Verilog. That's what I'm familiar with. If you learn Verilog, you have to make modifications. Okay? But yeah, we start out with modules. So I think I mentioned this in an earlier class, but I'm going to keep repeating it throughout the quarter. Use descriptive names in your Verilog for inputs and outputs, and also internal signals. Okay, like the node when we're connecting little modules together. Don't use like A, C, F, or just in, out, or like the internal signal. Don't use like just like a letter, like T or something. Use descriptive notations, because if you use very generic names, when you get the troubleshooting of that diagram at the very end, you've got like 50 to 100 signals that you got to look at on a tiny diagram and a sim. Everything A, B, C, and you're just going to go crazy. Okay, so you got to use descriptive names. Okay, so like here, even with the module name, I just don't call it box because there's going to be 5 other boxes. So I call it PCs. And you don't see all the idea. Okay, so like with any module in Verilog, variant outputs. Okay. Now, what type of logic circuit is a mux? Remember, we have these 2 categories of logic circuits. We have combinational logic circuits and we have sequential logic circuits. But which one of those 2 is a mux? Combinational or sequential? Fine. So how do we know it's a combination? What's an easy way to identify combination? You can possibly know it's like with certain volume power. A lot when it doesn't have a clock input, it's combination. Clock input always go with sequential. You need a clock and you have memory. Okay, so this is a combinational circuit, so it's a Verilog. And remember, this statement has what they call a selectivity list, which goes in parentheses. So, what input do you think I'm going to put here? What input is doing the, it's selector, but it's doing the sensitivity part of it, right? It's deciding what's going to be at the other. So, you see, you know that. Whatever I call that. Input, select input. Okay, and I just my option. So now in Verilog, system Verilog, you can write your value either as binary or decimal or hex. Okay, so I chose binary. So I would put take our 2 means 2 bits. It's like on the 2 bits. I'm using okay, so that's saying when this left is the 0, I'm going to assign my out. You're going to have something more descriptive out. Equal to whatever I call that in, I call that in just because I want to do something different. If you put a B, this is just sometimes instead of the. So, put it in binary. Now, this brings up something else that's very important. When we're in an always clone block, when we assign, you're using equal. Okay, that's called blocking. When we're doing a sequential type of circuit, we can always have that sequential. We use a non-blocking symbol when assigning. We assign the arrow. Okay, and a lot of times people are not conscious of this, like they'll just haphazardly sometimes do the equal, and other times do the equal with the arrow. But it's important that you get it right, because if you have these two statements, it's equals A, and then down here the same thing with using the arrows. So what is parallel versus parallel to in this model, just a straight line where A, B, and C are on that wire. You see, you have that goes like this. A would equal C. It's just basically connecting them all together, a wire on a bread, making it all the same voltage. Okay. But when you have those with the non-wire, it's not doing that. What it's doing is essentially putting circuitry in with the the circuitry could be latches. We see A would not equal C. There's circuitry. It's not like a wire. Okay? So you see, where that's important is if you're in a combinational circuit like that and you're using the wrong, like they put an arrow here, it's going to create a latch. So now you've got something that you want combinational, but you're going to get a latch. Let's put memory into a combination. And in 133, where most of the designs in 133 are relatively basic, and compared to this class, they're relatively basic, you could get away with that. You could get away with unintended latches in some of your combination circuitry because time wasn't a big issue. Time is a big issue in this class. So if you have any unintended latches in your order, it's not going to work. It may work, like individual modules may work, but then when you put it all together, because the timing is going to get all screwed up, if you get unintended latches, it's not going to work all together. So you got to be very cautious of it. In 133, you didn't have to be so careful. Though. Here you got to be careful. Okay. So you would just continue on with your options here. You have like G, pick mark, B, 1, out, whatever, one is called. And then you can just do the rest of them. And what you will always end up these statement with, what's like the final option? Default. The default. And that you let me want to time out. Not having default that also because of that. Another thing because of that is, let's say that you only had 3 inputs. So you just had this. You would still need 2 bits, right? You need 2 bits to identify the 2 bits. You need to it's in your case statement, you don't actually have something for that third input that can cause a lot. So you would treat that third input like this. You would still have a third input in your case statement. You would still put a few certain mark and then just put it out, equal some equal to make it seem well. You might want to make it you have a case statement where an option is not defined, that can be data latch. Okay. All right. So, and let's see. I think I talked about everything here. Well, to finish this, you would want to end. You can end over the beginning and one. Oh, yeah, we got to indicate first. That's all I'm doing. There may be some syntax errors, so I'm not even know. Yeah, so we indicates that we have it and put that. Thank you. Any questions on anything so far? Okay, well, also at 132, you talked about a register. What does a register do? Yeah, it stores data, right? You know, my 133 class, we use some registers to store some binary data, like signed data, little bit of pressure on looking that little calculator. Okay. So it stores data. And what is the register made of? It's a collection of what? Flip-flops, right? The flip-flop is the memory element, right? These flip-flops can store it. You put a bunch of them together, and that's what a register is. A register can store multiple states. And it's usually deep flip-flops. Okay, so let me a little table here just to show how this register is working. Now, I asked this from an earlier class, what does this symbol represent? It tells our systems what kind of input. Yeah, and RS stands for these RS. And let's say that these are actified. So both reset and load are actified and they're synchronous. Okay. Now, let's just say that the output of this register starts off with this data. Notice the output is 4 bits, also our input register is 4 bits. So let's just say, you know, in this part that I'm 0, that there's a binary 0, 1, 1, the output of that register. So that's what it's storing initially. Okay. And then let's say that reset and load are both 0s, they're both low. And let's say this is the data, the coordinate data that's at our input, 1, 0, 1, 1. So what's going to happen? Oh, the other thing is this is rising edge trigger. The register trigger rising edge on just like flip flops, but that's the data. So this is rising edge trigger. Right? So the 0 to 1 transition to the 5, the transition that matters. So let's say reset 0, load is 0, and then this 0 to 1 transition to 5. So the time of the 0 to 1 transition to 5, the deep value of reset and load. Yeah, why is it 0, 0, 1, 1? Right, if you have a register and you're not resetting, you're not loading, it's saving data. That's the storage thing. So yeah, our output would just be what it previously was. It would just stay what it had. That's when data gets stored, right? Actually, a register loading enables, or usually, I mean, there could be a case where you had 2 of them, and the enable is sort of like an override, if you will. Like if the enable is not enabled, it won't do anything at all. It's basically the same information, the same as the storage data. But usually you have either enable or both. But you could have both. All right, so now let's say reset and 5 load is 0, you still have the same data input, and now it gets blocked. So after the 0 to 1 transition of the clock here, what is the output going to be now? That could be all 0, right? Why? Okay, that reset. Right? Reset after high, so we data high, and it's synchronous. So when it's high at the time of the 0 to 1 transition of the clock, that's when the reset happens. And when reset happens, it makes the output all zeros. And that's what we mean by reset. Output goes to 0. Okay, let's look at this case. This case is reset is 0, load is 1. Okay, same data here. Okay, at the time of the 0 to 1 transition of the clock, what's the output going to be this time? Right, it's going to be the data at the input, right? Because when we load it, we're putting data into the register. So when you have a load for hardware, that's like writing data in, right? That's putting data in. And that's different than load instruction, right? You know, in the ISA for the Otter, when we have a load instruction, a load is a read, right? Getting data from, right? The store is a write. But in hardware, a load is like a write. Okay, that can be confusing. That's just the way it is. Okay. But yeah, our end now we are upright. We wrote. All right, then the last one is both reset and load are high. Now we get our 0 to 1 transition. What's going to happen here? Okay, I agree. All zeros get blocked. That's true. Like, what would you have to do in your Verilog to make it that? Okay, it could be done in the spacer. Now I'm going to have you. So what do we usually do? If reset is activated at the same time as the load, which one do you want to happen? The reset. And to make that happen, you have to make it the priority in your Verilog, right? So like in your if statement, that would come first. So provided that we made reset the priority, it would get reset resets. And that's what we want to do with your Otter. Any module that has a reset and a load, you want the reset to have priority. And you've got to make that happen when you write the code. It's not going to happen automatically. And so provided you made the reset priority, you're right. Okay. All right, so just bringing back some things from 133. This should all be stuff we talked about, right? It's not me. Okay, now a counter, a counter is a register whose output will just increment in binary, based on some inputs, and also it happens, the increment in the binary output happens on a clock edge, like here what's happening on the horizon, right? And so a counter, just like a register, it's just that it output either increments or decrements in binary based on some input, and also it happens on the clock. Okay, so in the system Verilog, if you're going to model a register, again, you would have the name of it. Now, like we said earlier, if you have a clock output, it's sequential. It's a sequential logic circuit. So in system Verilog, what kind of block did I use for sequential? Oh, that. Oh, yeah. Okay. So when you do your register using this thing, and I just said a moment ago, one that you said priority. So in my if statement, that's what I would start. Right, the reset is high, so the reset now. If we can active low in Verilog, information report, but we got to active high. I'm pretty sure in the Otter, all your inputs are active high. I don't think we have any active low. Okay, so if we said we just assign your output kind of on, so what we're gonna use here. I could put, you know, 4 big mark B and then 4 zeros, but what I tried to do here was use X, right? Because how many X characters do I need to represent 4 bits? It's 1, right? So it makes it easy, a little easier. So when we put 4 bits in the 4 bits, so we put X, I put in H, and then it's just 1 character 0. Right, yeah, you'll do that in the sim file. You know, in the design file, you just define plot. But yeah, as far as what frequency it runs at, when you go to sim it, you're putting the period that we're going to use. And we're going to use, well, at least for this here now. Well, what we'll use for the clock period, the reason I'm hesitating is because later on we're going to get the cases where in order to do a sim, you need more than just one clock pulse to see what's going to happen. So things happen in different clock cycles, whatever. But we're going to use a period of 20 minutes. The reason for that is the basis 3 board, it runs at 100 megahertz, the 10 nanosecond period, but we're using half that, basically 50 megahertz. And that's to give some leeway, right? Because if, you know, if for some reason your design was all good, but you know, it was just requiring a little bit more time than what's necessary, by using half, essentially half the clock frequency, it gives some wiggle room. And you'll see that when we get to the point where you actually put your design on the basis board, there's something else that surrounds, basically surrounds that Otter diagram that you see that divides the frequency by 2. Basically, slow it down. Anyway, the short answer to your question was the clock speed we're going to use in centimeters. Okay, so this takes care of the reset. Now we're going to take care of the load. So I have an L2. Remember with if statements, you can have 0, 1, or many else's that you want. Here we're going to count this 1. So if it's not resetting but it's loading, then we're going to set the output whatever we call it. Again, in your code, the program, you're not going to use just in now, right? You're using the script. I'm just using generic here because this is an example. Well, you do the same thing for your hardware too, right? You're going to be unscripted. Okay, then I just end this. Why am I not putting an else? Right, because remember, that's how you can generate a latch in Verilog or System Verilog. You have an if statement without an else. So you see, we're not resetting, we're not loading, we're storing. Okay, by not having an else there, that's stored. So remember, in Verilog or System Verilog, slash is a comment. So no else equals stored. Here we want a latch, but this is the register. Okay. And then, all right. So any questions at this point? So yeah, if it's active low, you can just put an explanation front that makes it active low. But like I said, in the Otter, all that we put them, I'm almost 100% high with car. All these are active high, there's no active low. So you don't have to worry about it. But that's how you do it. Yeah.
So it would be this line.
It's a squiggly line if you're talking about a bit. Like in Verilog, the inversion, like the squiggly line is when you're talking about a bit. When you're talking about like this is like a symbol, like some people call an input, then it's an exclamation. Exclamation. Yeah, there's like bitwise symbols and there's I forget what they call the other bit symbols, but it's when you don't have this. Okay, so up to this point, this is all been stuff that is 133, right? Well, that's what you need to build this program counter. Okay? Because this program counter is a register along with the mux. It's a register that counts, but like you said, a counter is a register that just increments the binary. Okay. Now, what is the purpose of the program counter? Because I did talk about this last time. What is its purpose? What is the program counter providing for that dollar? Well, it has a clock into it. And this is the clock into it. But what is its purpose? Because remember, the output of the program counter, it goes to memory. There you go. Yeah. The program counter is providing the address of the instruction to be executed. Right. And it's going to increment by 4. Right? Because word addresses are separated by 4, like we talked about. When you see the purpose of the program counter is that it provides address of instruction and stuff. The output of the program counter that has the address of the instruction being executed, it goes to this input address 1 of the memory module. And remember, the memory module, that's where the instructions are, right? And that's where our memory is, right? And, part of memory is the code segment. And the code segment is where the instructions for the program are. And that's also the subset, number 5, problem with the subset of that memory. Right? But the problem is the actual device that has the code segment for the instructions. So the PC is just a register. So the code that you need to model this program counter is going to look a lot like this. Now it has a mux also. And the code you need to model that mux will look a lot like this. Okay. Now there's this block. There's this +4 block. Diego, right? Your name, Diego Bob, why is that +4 now? Right? Because remember, where the code is, right? The code segment around inside the memory. Every instruction is 32 bits. And that memory is byte addressable. Right? So each row has 4 bytes. So because the instructions are 32 bits, and because it's byte addressable, the instruction addresses are word addresses, and they're separated by 4. So your first instruction is going to be at address 0, your next instruction is going to be at address 4, and your next instruction is going to be at address 8, and your instruction is going to be at address 12. So you see, the output of this program on where the address is connected to this +4 because after an instruction has been executed, you want to increment that address by 4 to get the next instruction. Right? Because the instructions are separated by 4 and address. Okay? See, that's why the +4 is there. That's what makes it a counter. Right? See, it's counting in 4s. Okay? And you see the output of that block, where it's incremented the address by 4, is one of the inputs, the mux, that goes to input of the PC. Look at what the other inputs are. Now, we haven't talked about most of them, but you've seen one of these already. You saw this JAL as part of the last assignment, right? What kind of instruction is JAL? What does the J stand for? Jump. A jump is an unconditional, what we call an unconditional branch. And it's when you're not going through the program sequentially, right? If you're going sequentially, you know, you get the instruction at 0, then you get the instruction at 4, then 8, and 12, and so on, right? But if you don't want to go sequentially, right, you want to jump, well, that means your address has to change by something than 4. Right? So you see, that's why there's these other inputs in this lots that go into this program time. Sometimes you don't want to go sequentially with the program. Sometimes you want to jump. These are kind of jumps that eventually we'll learn about. But any kind of jump, you're just not going sequential. A branch, we're going to talk about next time. A branch is a conditional jump. And then there's these other two that have to do with something called interrupt. You know, I'm still going to have you put it in there in case we have time. Okay. Now, another thing to look at, another thing to notice, look at where the select line. This is our select line of the month, right? Select. It goes to PC source, something called PC source. Can you see on your diagram where PC source is? Does anyone see it? Did you find it? Where's PC source? So PC source is here, going to the select line and not, but where else on the diagram? But there's another module that yeah, up in the upper right hand corner. And output of the CDR, that's the for decoder. That's the control unit decoder. And right above it is the control unit FSM. What does FSM stand for? You have plenty of experience with that in 133, right? That was like the climax of 133 FSM. So yeah, we have this control unit that's split up into two parts. FSM, which is sequential, and decoder, which is combinational. If you look at the outputs of the decoder, the control unit decoder, most or all of the outputs go to select lines of the muxes. If you take a look at like the PC source for the box, there's another one called like source A or something that goes to the mux near the ALU. There's like a source B. Now also, one of those outputs is the code goes to the ALU itself. It means ALU final. ALU is that what it is? I think I'm not looking at the diagram. Yeah, you'll see that one of those outputs of the decoder goes to the ALU. And the reason for that, you're going to see this in a couple of weeks. When you model the ALU is going to be a big box. Like when you model the ALU, it's just going to be a big piece thing. Okay. So yeah, the outputs of that decoder, the control unit decoder, goes to all the select lines of the muxes. And then look at the outputs of the FSM, the control unit FSM. What do you mainly have there? What kind of outputs? What's that? Okay. The outputs of the control unit FSM. So right above the control unit decoder, there's an FSM. What are those outputs mainly? Like, do you see PC right? So what kind of most of the outputs of your control unit FSM are reads and writes. So like for example, PC write comes from the FSM. Okay. So you know, this isn't for a while. In fact, this isn't for several more weeks. But what you'll see, and you'll see why those modules are called control units, is that That FSM, the control unit FSM, along with the control unit decoder, they control how the data passes through all the other components in this audit. So PC source that's coming from the control unit decoder, the PC and then the PC read that's coming from the control unit FSM. I just wanted you to know that now. Okay? Like I said, as we go along through the course, I think it'll become more evident, how it all ties in. Okay, so we're almost done here. I can see what else I want to say. So really, the last thing here before we stop and you can start your assignment is just to talk about the assignment itself. And I should turn my camera. By the way, if I forget to turn my camera when I get here, can you remind me? Oh, even though I put that note there, a lot of times I'll still forget. There we go. So last time I had it in the same color as everything else, and I think that's why I missed it. I think red helps it stand out. All right, so you're ready for hardware number 2. Okay, hardware number 2 is building this. You need a Verilog or system Verilog. Whatever you learn, you want to that the grading criteria for the hardware assignments are on Canvas. So, yeah, the first hardware assignment that you turned in last night, that was different than all the other ones, right? But now, starting with this hardware number 2, if you look at the criteria, you're going to see there's 3 main criteria. The first one is making sure that the elaborated design, the schematic that Vivado gives you looks like what you intended, something like this, along with not getting any latch error messages, well, no error messages, and no latch warnings or other significant warnings. Now, people in my 133 class, you may remember that in the constraints file for the clock, there's like 3 lines at the top of the constraints file for the clock. And what I had my 133 students do is only uncomment the first 2. I had them leave the 3rd line comments. I talked to Dr. yesterday, and it's actually better to have all 3 of them uncomment. When I first started teaching 133, the professor that I was basically following their process of people. They always their mind uncommented, and I thought that was the thing to do. But it's actually better to have all 3 uncommented. You don't get less warnings if you do that. If you get 1 comment, you get a lot of tiny warnings. Again, even though in 133 it was okay to get tiny warnings, here you can get a problem. So anyway, top 3 lines and how to plot the top 3 lines uncommented. Okay, so that's like one criteria. Then see what's the other one. And there's test cases. That's an important course. Remember, test cases. This quarter you have to come up with those, and you want to have enough test cases that show the whole functionality. If you don't have these 7 loads active at the same time. Your test cases, you would want to do that to see what happens. Right? As long as you can use it, pretty well, you get these. Okay, so that's just an example of what I mean by kind of break it. So yeah, there's test cases along with showing the timing diagram. And then I think the last criteria is actually showing your code. And there you just want to make sure that you have sufficient comments. Okay, I told the ISAs to look out for that, because sometimes people don't put any comments, but you should have enough comments where, if you come back to it at a later time, you would understand what you're doing. Okay. So anyway, actually look at it. Don't take my word for it. Actually look at graded and complain about it after. Okay, now there's basically two approaches to this design. The two like the review approaches. You can do a structural model. And in my CP 130 class, 133 class, that's what we did the majority of the quarter, other than the first couple of designs that were pretty simple. Everything else was structural. So if you're doing a structural design, you would have a file for the MUX, a file for the register, and then an overall file like where you connect them up, the lower level modules together. And recall that you need internal signals. In fact, how many internal signals are we gonna need this design? Remember, internal signals are what connects the lower level modules together. But how many internal signals would I need here? Okay, which ones? All right, yeah, this is definitely. So again, I'm not going to use a descriptive name here, but you are. Let's say, I'll just say this is P1. But you're going to call it something else. Like you might call it, I don't know, Mux underscore response for actually writing out something like that to show what's getting connected. Okay, here's another one. Yeah. Definitely would have a thing called connected like to the level pattern internal signal because I was on lower levels like a higher level input clock, which you don't need internal signal. The internal signals are just when you're connecting lower level blocks. So where else would we need? Yeah, you need one here, but you need one more. You need those two, but there's one other one. And here, this is also. Because you're connecting this out to this lower level to with the input of this lower level. It's just like a block. Okay, so yeah, you're going to need some internal things. Now, the model on the boardwalk, we don't want you to make like an RCA, you know, with 130 with a 4 or something like that. We don't want you to do that. Okay, we want you to let the software do the work. So that boardwalk, you're just going to use an assigned state. Like if you do the structural model, you can have an assigned statement in this top module where whatever you call this internal signal, you can just assign this internal signal to this internal signal plus 4. And you're just going to multiply 4. And then Verilog will do the work. Verilog will put in the adding circuit that it needs. But we don't want you to like build an RCA for this. You could, but that's, you know, we're taking advantage of the power of Verilog here. Letting software. Okay, so that plus 4 is going to be unlocked. It's going to be assigned. So that's one approach, a structural model. Now, the reason I put these two approaches is because depending on what instructor you have for 133, you might not have spent as much time doing structural models. Because the 133 instructor is doing different than what I do. So it can also be not a structural model where basically this is all in one module. And you put all the code in one module. You get a still every outputs and their internal signals. You must code in your register separate files. They're all in the same file, and then you would still need your internal signals and you would use assigned statements. You know, again, you use an assigned statement for this plus 4. Did you have a question? Yeah. Each new person groups go through the software and hardware up until like after the meeting. So, because at this point you should be ready to start working on this. Okay. All right,